So I spent 5 months building this innovative oscillating belt sander with a height adjustable and tilting belt. Made a quite detailed video about it, but it doesn't even work. It's not like anything's already broken, but I screwed up this belt tensioner so badly that it's unusable and I need to rebuild it from scratch. And as optimistic as I am, I thought this would be a quick fix. Oh boy, I learned my lesson. I had to rebuild this 4 times until I got it right. And every single version taught me a painful, valuable lesson. That would be the second fail. I'll give this a 50-50% chance of working. Fail number 2. So let's go back to the beginning, solving a seemingly simple problem. The first problem is so painfully stupid. I still don't know how I could let that happen, because I screwed up the roller distance. A used belt that's a little stretched out goes on there no problem. A slightly used belt is a little more challenging, but okay. But a new belt is just painful. And you want to know why that happened? I'm a naturally good designer. No need for testing. Wrong, you idiot!
So to fix this first issue, I 3D printed some dummy drums, which I then also turned to the exact diameter and punched out a few pieces on the CNC router to set up a simple test for decreasing drum distances. It starts at about 0.5 mm less than the original, with the matching parts on top.
Now I can test how easy it is to put on a new belt at different roller spacings, but not forget about the tension roller, because when the belt is tensioned, these 2 sections of the belt should be roughly parallel, because otherwise it could collide with the table at 45 degrees. So just going with the closest distance on my test isn't the answer. Although a new belt would go on super easy, a used slightly stretched belt, when tensioned, would definitely cause other issues along the way. So I now need to find the spacing sweet spot, which is the best compromise of easy enough for a new belt, but not too close of a distance for a slightly stretched used belt. That sweet spot seems to be 216, which is 1.5 mm closer than the original. And I can now use this to update my 3D model of it, because everything else is based around this distance.
And here's where that distance lives. This straight section of the belt sketch. When I add this up with all the other sections of the belt, the theoretical belt length comes out to be about 607, which is less than the stated 610. But the test showed me that there's a length range between a new and a used belt.
Okay, now that this is fixed, I can tackle the actual issue. Because the big problem from the beginning was the belt tracking, which means making sure the belt tracks centered on the rollers and doesn't move up or down.
The way other belt sanders on the market do that is by tilting one of the 2 rollers. I chose a 3-roller design to have 2 of them stationary for sanding curves against and have the third movable for belt tensioning and tracking, which I also do by tilting the roller.
And the concept works, but the response time is so slow that I'm constantly overcorrecting in one direction or the other. And getting it right just takes forever. When I'm swapping to a different belt, it's all different again. That's just horrible. Also, when the belt is moving too far down, it starts catching here on the frame and then it's not coming back up. So to fix that, I need to design and build a better working tension and tracking system that still fits in this tiny space here, because I can't redesign the whole thing. It's gonna be a challenge. I have 2 ideas in mind, but instead of just starting to build anything, I think it's worth exploring why this doesn't work as well as this one.
Both mechanisms tilt the tensioner roller. This one like so, and my one like so. But this one is way more responsive than my tensioner. Why? Well, when you look closer at the actual movement, you can see that here the roller is moving a lot more side to side compared to mine that's basically just tilting.
And I think that's a key point, bringing more actual movement into the roller instead of just tilting it. If we look at the movement of this roller, it seems like it's pivoting around a point right about here. Let's have a closer look. And there you can see it. This is the pivot point. And that's the whole tensioner. Comparing this to my tensioner, you can see that here the pivot point is way closer to the roller, which results in way less movement and basically just tilting it. You probably think the solution is simple. Just move the pivot point here further back as well. And yeah, that's basically the idea. Along with a few other subtle changes, but I'll get to them during the build, so let's get started.
To get this improved concept into an actual part, I started with a really rough 3D model of simple blocks to get an idea how it comes together, and then refined it into a detailed model. All parts should eventually be made from metal, but for a first prototype I 3D printed most parts, and while they are printing I can take care of the lathe parts. Similar to the original, I need a pivot shaft with a flat and threaded holes, and that's not too complicated. First facing some stock to length and turn the ends to a precise fit with some reamed bushings. I also got a great new helper for deburring and getting shiny surfaces.
These are the Proxxon belt and tube belt sander, and they are useful for all kinds of tasks. You will see.
And stick around to the end, because Proxxon is giving some of them away. For the flat, I put the shaft into an empty tool holder, and for this size, the clamping screws work just perfectly. Then moving the compound sled to the middle, trimming it in square, chuck up an end mill, adjusting the height, touch the part, set the depth of cut, and then sand it. The threaded holes are just a matter of scribing the positions with various marking tools and drilling them. All done. The next part isn't interesting, and I guess you can imagine how I made it, but these two parts are more interesting and also pretty small. One gets a precise stud and M3 threads, then cut off, cut to length and deburred, and then back in the tool holder to cut another flat, and finally M6 threads right through. The other piece is a special brass nut, so I turned on the diameter, drilled a threaded hole, cut to length and milled another flat, except this time on both sides, which turned out really good and fits a wrench. The last metal part is the tension roller itself. Like previously, I made it from some thick aluminum tubing, then just facing it to length and turning the precise bore for the bearing. For the installation, I heated the roller in the oven to expand it so the bearing would just drop in place. At least in theory. In reality, you often need persuasion. Now the 3D prints are also ready, and I can finish them with the reaming and cutting threads.
Although this isn't the best way of working with 3D prints, since I also have melt-in threaded inserts that would make way stronger threads, I would design the parts a little differently then. And as eventually everything is supposed to be aluminium, I'm now just treating everything like it is aluminium.
But now some assembly, which to me is one of the most satisfying parts. Seeing your own pieces come together is just delightful. The assembly has two main parts, one for belt tension and one for belt tracking. And here they get joined together with a shoulder bolt.
That shoulder is supposed to poke through. Otherwise this washer has too much play.
That's fail number one, with an easy fix.
Yeah, that's better.
There the wheel can tilt, so let's add the knob, which is also where I need that little brass nut.
So with the screw I can pull it up in this direction, but it cannot push it in the other. So here will be a spring that will keep it constantly tensioned in this direction. But the spring doesn't fit. That would be the second fail.
And I also noticed that this L bracket should be stronger, which means two new parts. But at least the spring fits.
And now the spring loading works. So with the fails, this prototype is done, and I'm glad this happened now, because iterating with prints is super quick and cheap. Imagine having wasted the time and money if this was aluminium. But before going any further with testing, I mentioned that I had two ideas for the tensioner. Because with this concept, I'll tilt the wheel in this direction like so. But what about tilting it like so? Could this work? I don't know, but I want to find out.
So I came up with the second design, made all the parts, a few fails as well, and assembled them similar to before.
And now I've got two similar assemblies, Team Blue and Team Red, that function quite different from each other. But to test them, I kind of have to build the entire assembly that fits the machine. This one unfortunately won't work because the new mechanisms don't fit in here anymore. And to make it even worse, the two mechanisms are different enough from each other that they will both require their own assembly. Ouch.
So the printers had to go overtime, making all the parts necessary.
At least I now have a second printer, the Prusa Mark IV in my arsenal, which speeds things up a lot. You may wonder why I printed the new parts instead of cutting them from wood again, because it takes about 20 minutes to cut one and 2.5 hours to print one. But you can't forget about programming the part, which takes a lot of time, and the printer I can just let run overnight. So considering all that, printing is faster and simpler.
But I had to finish the prints with a few threaded holes, which is somewhat annoying, because you have to do it slow so the threads don't melt, opening up the countersinks a bit, and then assemble the parts. So pressing in bearings, fitting bushings and set screws, and bolt the parts together. The overall construction isn't much different from the original, just a specific placement of components and a few simplifications. The idler drum I can borrow from the original, but the drive drum got an update, so for the tests I had to print a new one, turn it to the right diameter and make it fit the bearings. The tensioner, or rather tension quick release, I can also borrow from the original since that worked great and needs no changes. So then the top plate gets screwed on and the tracking adjustment knob which tilts the roller. And as you can see, there's now a lot more movement.
So far so good. One more problem before testing. This plate here, acting as the spring that applies the belt tension, because it's 3D printed, is too weak and needs to be stiffer. On the original version I used a steel plate, which was kind of too stiff. I tried to weaken it with these slots, but that didn't really do much. The only thing that will help is making it thinner, but I don't have the material on hand, or make it longer. Because the longer a spring is, the springier it will be. So I now have to make this plate longer without actually making it longer. Here's my approach to that. With all these cuts, the overall dimension stays the same, but the effective spring length gets a lot longer. Now I just have to make this from steel. And for such delicate work, I have a fantastic new little tool, mini angle grinder.
Another Proxxon tool with which I have incredibly good control, perfect for this part. After cutting the steel to size, I spent some time marking all the holes and then spotting and drilling them. Then I marked all the places for the slots and went to work. Some of them I could cut all the way from one side, but the really short ones I had to do from both sides. Once finished, I'm left with many burrs that I normally would have to file away by hand and patience, but this little tube belt sander with the satin finish belt works perfectly for this as well.
Now I got it installed and also replaced this part here with a steel one, so everything here is mounted to something nice and rigid. But as I was reassembling it, I realized this will never work because I made a fundamental mistake. I'll test it anyways and then tell you why this basically is a piece of garbage. Tensioning a belt works, so let's put that on the machine. For now the motor is disengaged, so I can first try it slow with the drill. Belt is wandering down. And now it's coming up again. That works. Now it's too far up and yeah. Now the adjustment knob comes out. Yeah, I already called it a fail, but here's why that happens. It's all because the pivot point is in the center of the roller, because for this whole adjustment thing to work, this knob needs to be constantly pulled down. In idle state, this little spring does that job. But once the belt tension is involved, there's an evenly spread force across the roller. And when it's centered, that force presses directly into the pivot point. Everything's fine. When it slightly shifts down, that force shifts past the pivot point, trying to tilt the roller like this. Like the spring, everything's fine. Then I adjust it upwards, belt moves upwards, and that force shifts past the pivot point on this side, which will tilt the roller like so. Then the knob is loose and I'm screwed because that's not coming back down. This little spring can't do anything against the belt tension. One solution would be to put a nut here so the adjustment knob can pull and push, but there would always need to be some amount of play causing other issues. So in conclusion, this is how not to do it. On here, where it's done right, we could already see the pivot point is roughly here. So no matter where the belt is on the roller, the force is always past this side of the pivot point, which will always press the roller into the adjustment knob. Right now it's the idle spring, but with it removed and the belt tensioned, it's still the same behavior, no matter where the adjustment knob is. So this tells us the pivot point being off-center is crucial. And you know what's weird? I already knew that when I built the original version. Here the pivot point is off-center. That's why this kinda worked.
So let's get this out of the way for Team Red.
I'll give this a 50-50% chance of working. Let's see. Track's okay. It moved up a bit. Let's try adjusting. And the knob is loose. This doesn't work either. Fail number 2. What a disappointment. I spent a lot of time designing and building them, and both of them being a fail. 3 fails, if you include the original, is just tempting to just screw the whole project and move on. But being that low in a project of this extent, it's important to not get emotional and try to objectively analyze what went wrong. I mean, I figured out 3 ways of how not to do it. They can now tell me what is actually important to start over from scratch and get version 4 working.
So far, I've learned 4 key elements. The first is moving the pivot point as far behind the roller as possible, so it's more moving than tilting. Second is to put it off-center, so the belt tension always wants to tilt the roller in the same way.
The third one I noticed on this design as well, and it's to spread the pivot point and point of adjustment far apart to make it more rigid. Because as you can see, this turned out rather flimsy. Of course, this would be much less of an issue if these parts were aluminum and not 3D printed, but it would be just much better to avoid this problem all along. Like here again. Here's the pivot point, here the point of adjustment, and this obviously is perfectly rigid. And also decoupled. And fourth would be to use a crowned roller again, because a belt will always move to its center and find a neutral state there. Problem is, that's a little more involved to make, so I'll first test it with a straight roller.
So back in CAD, it was easy to shift the pivot point, but coming up with another adjustment mechanism was more difficult. I first thought of some lever type mechanism, which I wasn't happy with, but a sliding piece and ramp seemed promising, and that's what I went with. And with just a few iterations of every single part, I have this prototype ready for testing.
And I have high hopes for Team Green, because the pivot point is now as far behind the roller as possible, off-center, and the point of adjustment is on top, also decoupled. This just 3D printed feels 10 times more rigid than Team Red and Blue.
Here it's working, looks way simpler and smoother. The spring plate concept from before worked great, so I could reuse that, and then it was just a matter of building the rest of the assembly, which also needed 1 iteration.
Quick interruption for exciting news. I'll be moving into a bigger shop soon. Finally, more space. I'm renting a place with these 2 guys, you maybe already know, and we're doing a lot of renovation at the moment. And I try to cover as much as possible with videos and post them on a second channel called MH Anything. And it would be really cool from you to jumpstart that channel from like 0 to tens of thousands of subscribers instantly, just for the fun of it. And once the move is over, I'll also post smaller projects and try out different things that won't match this channel here. But for now, moving content, very exciting. Back to the project. Time for testing. Okay, it moved down. I can adjust it up. And I can adjust it down again. Yes, it works. Okay, now this works like the original, it's just way better. It's actually responsive to an adjustment I make. Something happens immediately. The problem still is, it's very hard to get it centered on the rollers where it then stays centered. And that's what the crown roller should solve.
To better understand what I mean, I set up this simple demonstration.
With a flat roller, I can adjust the tracking by tilting it, like on my tensioner. The problem is, even a very slight adjustment will make it track all the way up into the frame or all the way down. It won't stop. To get it in center, I need to have perfect alignment when the belt is in center. And when I now throw it off, it will stay down. If I throw it up, it will stay up. It will not come back to center unless I do another adjustment. Now with a crown roller that has a curvature, I can do the same kind of adjustments by tilting it. But it, as you can see, always tries to center the belt. If I do a slight adjustment up, the belt moves up but eventually settles. If I do a slight adjustment down, it also eventually settles. And if I move it straight, it centers in the middle. If I try to throw it off, it will find the center by itself again. The reason this happens is when the belt is off center, the side towards the center has more tension, which puts the belt into a curved shape. But the belt doesn't want to be in a curved shape, and since the pulley right now is pulling more on this edge than on the other, and a curved shape, this force imbalance pulls the belt back on center until it's straight again. And that's the exact behavior we want on a belt sander, and why the adjustment roller needs to be crowned as well. But now machining this curved profile is impossible with a manual lathe that will only do straight cuts. But I can approximate it with a few angled straight cuts. This is of course exaggerated, the actual angles are very shallow and accurately represent the curve. But accurately setting up a 0.57 degree angle is not possible with this scale. However, we can use a dial indicator and basic trigonometry. When I move the sled 90 mm and read 0.895 mm on the dial indicator, this angle is set up.
I chose 90 mm because that's 3 turns on my hand wheel. And then it's a bit of back and forth with the light hammer taps on the compound sled until the dial indicator tells me what I'm looking for. One double check after tightening, looks good. Now the roller goes onto a shaft with a drive dog and a spring with the life center to support the other end and press the roller against the chuck. Then I started with a light cleaning pass, followed by a Sharpie mark and then a 36 mm scratch mark. That's exactly where the angled cut needs to start. And once there, I cut the whole length with a spring pass back. Flipped around, I can do the same to the other side and then set up the second angle. It starts at an 18 mm mark, everything else is the same. And with a light chamfer, the part is done.
If everything went right, the diameter on the outer edge should be exactly 1 mm less than in the middle. In the middle we have 29.89 and on the edge 28.91. That's pretty damn good and also extremely close to the actual curve. Okay, let's see if it works, and this time with the motor, not the drill. Moving down, moving up, too much, and not quite there yet. Let's try more belt tension.
Next test.
Interesting, the adjustment knob started moving on its own from the vibration. But I can adjust that, because right here at the other end of the adjustment knob I have a nut that I can tighten a bit more. Even better, I installed a spring washer so there's constant pressure on the knob. Okay, and with that done and more belt tension, it starts getting better, which makes sense. Because as it's now, the effect from the crown roller depends on two things. The belt tension obviously, the more the better, and the amount of angle that the belt wraps around. Also, the more the better. Here again, it's 180 degrees, which is ideal. On my one, it's just like 20 degrees. So I don't need a lot of belt tension, but as you can see, this spring plate is too weak.
So I made a slightly stiffer one, but unfortunately this didn't work. I also made an even weaker, thinner plate to see if it gets worse, which was the case. So then I made a thicker one without the cuts that's now almost rigid. Finally, progress.
But there's still this weird behavior where when I have the belt centered and stable, it randomly starts moving again and won't stop. And this is because the way I designed this tensioner is not stiff enough. There's still movement in the parts from flexing, and that's causing the weird behavior. Now, leaving the tensioner for a moment, there is another solution to this problem.
And it's to swap the straight idler roller with a crowned one as well. So now the centering effect comes from 180-degree belt wrap as well. And would you look at that, it works.
And I knew the whole time that this is a solution that works, but I've tried to avoid it at all costs because I wanted this roller to be straight to properly sand against it. Now that it's crowned, I can't be sure that the parts that I sand against it remain straight and square. So I have one more idea for a tensioner, and if that doesn't work as well, I'll use a crowned roller here as well and move on. Team Black should now solve the two remaining issues, which are flex in the hinge, and the other is the unwanted twisting in the whole assembly, because having this plate be my spring for the belt tension, it had to be thin enough to be springy enough, but this unfortunately caused the whole assembly to no longer be stiff enough. Here I now try to make it as rigid as possible with a 3mm steel plate here and here, the spring plate being separate, and this hinge design, now also being mounted to 3mm steel, should no longer flex. It's a pretty interesting part, so here's how I made it.
The hinge pin is a steel shaft. The small angle grinder is perfect for parting off small diameters of tough material like this. It also has a flat and threaded holes. The hinge body is a solid 3D print with a reamed hole, where I then removed the top section until there was enough clearance for the hinge action. No more flexing here.
But will it work? That looks good. Finally. But this was never the end goal. Just a prototype. The 3D prints wouldn't last very long in use. So now comes building it proper from aluminium. And for that, I'm very glad to have JLC 3DP back on board providing the parts. Because when you look at some of them, they are pretty complex. 3D printing them was super simple, but now CNC machining them is a whole different story. I mean, I have a CNC router with tool changer, which I basically used to build the entire machine. And also this complex part was no problem, but that was wood. Aluminium is a whole different story. I've used it a couple times for parts. It works, but it's not great. So I'm more than happy to use the CNC service JLC 3DP provides. I'm also pretty sure to get good results, because they already made the table surface plate for the machine, and that was flawless. And while I'm waiting for the parts to arrive, I can make the new drive roller myself.
I've shown this process in the first build video, but there are a few changes to the part, so it again starts with 3 blanks cut from a bigger plastic sheet offcut. At the lathe, I then faced it and turned the first bit round to remount it the other way, so I could face it to length and add the stud for the bearing with a precise dimension, because the bearing needs to be pressed on. Then, without changing the setup, I drilled and turned the bore to a precise fit as well, and repeated everything for the other 2 parts. Now I needed to drill some holes at certain locations, for which I printed and turned some templates that fit the outer and the bearing diameter. With a transfer punch, I obviously transferred the hole locations to all parts, which I made the same size to only need 1 template. The 6 holes at the bearing are for interacting with the drive block, and the others are for bolting the 3 parts together. So through holes for the outer parts, followed by counterbores, which is a neat operation. All you can see is chips, and then the bore is done. The middle piece gets threaded holes. After that, the drum gets assembled on the main shaft with bolts and spring washers from both sides. That aligns the parts to each other perfectly, and I can constantly check if the drum still slides easily. Now at the lathe, I use a drill bit as a drive pin. Slide the drum onto another shaft and place the life center with a few bevel washers to press the drum against the chuck. Like this, I could turn the whole drum to its biggest outer diameter. And turning plastic like this is a bit of a double-edged sword. It turns super nice and is easy to achieve target dimensions, but the chips, or rather chip, either makes a big fat rat's nest around the chuck or wraps itself tight onto your part. It's a bit annoying, but okay to deal with. Next is the channel for the rubber rings. I probed the left edge, moved the sled over a bit, plunged in 1 mm and went ahead. After 4 passes that was done and I could finish up the left and right side, making the channel almost perfectly 100 mm wide. That was all the turning for now, so I could remove one side again to install all the rubber rings, which are the grippy material driving the belt. These are also 3D printed from flexible material, slightly undersized, so they would stretch and clamp on the drum.
One important detail here is the exact diameter of the drum and the rings. Because these rings being printed, they have the layer lines, and when I cut my final diameter, I should cut at exactly half of a layer line and not in between one of them, because if that happens, the layers could kind of break apart like on my test drum. I of course made a test piece, and on the 3rd try I got it right. This is the final diameter that the drum needs to be.
Back on the lathe, I could turn the rings to final diameter. Despite being soft, it cuts pretty well, but you need to use sharp tools and a minimum cutting depth of about 0.2 mm, so the tool can properly bite into the material.
Right now the surface is kind of rough, and that's exactly the transition from one layer to the next, but I still have material to cut away. After the final pass, now the surface is nice and smooth.
Now the reason why I designed a new drum is this chamfer. A small detail that makes a big improvement once everything is assembled, but for now the drum is complete.
The other part I need to improve is this cam-shaped piece, because until now this was steel-on-steel friction, and as you can see this did a number on both parts. Grease as a lubricant isn't really an option, because combined with sawdust this will eventually turn into some sticky goo, so a much better choice of material is a bearing bronze for the cam.
Like brass, this is a wonderfully easy material to machine. Every cut leaves a nice surface. But the important feature is the eccentric hole, which I could achieve with a 3 mm spacer on 2 chuck jaws. From there, it's just like any other hole. First center drilling, and finally reaming. Then I roughly marked the placement of the clamping screw, eyeballed the position in a tool holder, as well as the vertical tool alignment, and then everything that could go wrong went wrong. I forgot to press record, the battery died mid-shot, and then my memory card was full. Hooray! All the threaded hole machining went well, but nobody will ever see a recording of it.
At least it's done, which is good, but even better, the parts from JLC 3DP arrived. It's safe to say they are well packaged and protected. And of course, at first I want to see one of the big complex parts. Oh, nice. Now, if this isn't an upgrade, I don't know what is. The cut and surface quality is just beautiful. All features, also one in the edges with threads are there. I've even got some parts anodized. All parts are clean, there are no shavings, no burrs, no cutting fluids, they aren't oily. My hands are clean, just a bit aluminium smelly just from handling them, but this is all ready for assembly. That's super cool. And I mean, my 3D prints got me through the prototyping phase of this project quickly and reliably. But if I now think making the actual machine part myself, with my current equipment, even the CNC router, I don't see it happening, especially not in this quality. And that's why I like having JLC 3DP as a sponsor, because without their service, I couldn't have made my crazy idea of the sander a reality. I can only recommend checking them out. The link is in the description. And by the way, this is not everything I can show you. There's another package waiting. But first, some assembly. First, the bearings go in, and this is the only unfortunate part because the bearing seats are a hair too big. To be fair, when I ordered the parts with a drawing that contained the bearing dimension and tolerance, they contacted me back saying, hey, we maybe not hit this precise dimension. To which I replied, Well, just go for it. I'll figure out what to do if that happens.
So I figured that Loctite should solve the issue. I cleaned the surfaces with acetone, spread a few dabs on the bottom surface, a continuous bead around the bearing, and dropped it in place.
12 hours later and the bearings are secure.
Most of the assembly didn't change much, but here I'm using plastic bushings and ream them after the installation for extra smooth motion. The front plates I assembled on the table saw, which ensures everything is flush and square. And in addition to that, there are also 2 steel shafts on the back. The thicker one also got a hole for the tensioner return spring.
Now a nice little upgrade for the idler roller, because after the test in the beginning, where I figured out the ideal roller spacing, I'm still not quite sure if that really is ideal. And since I don't know what's perfect, I made it adjustable. So now it is a slot with threaded holes for set screws. And to reach that, even when everything is assembled, there's an access hole through the shaft.
Next, the tensioner, starting with a new knob that now is anodized aluminium. I've assembled this exact unit before with 3D prints, but doing the same with aluminium parts is so much nicer. Here's another small detail. This tiny hole prevents air from being trapped inside the hole when fitting the shaft.
And now the last part missing is the ramp, but this shape would be extremely difficult to machine, so I got that 3D printed in different materials. Now I have my version printed with FDM from PETG, this one printed with SLA from resin, this one printed from SLS with nylon, and the metal printed one from stainless steel. They all come from JLC 3DP as well, with exceptional print quality. And I got those 3 versions because I didn't know which technology would be the best for this part. I was looking for the smoothest, and that's definitely the SLA part. However, I would really like to use the steel part, obviously, but I need to get the surfaces smoother. Give me a second. Not too bad.
The last part on here is the spring plate for the belt tension. So I got some thin spring steel plate that only needs 3 holes. The problem is spring steel is so tough to machine that it broke a spot drill, a carbide carving bit, a center drill, a normal drill bit, and another carbide carving bit. Then I realized the holes don't need to be holes. Grooves are sufficient. What an expensive lesson learned.
And with this complete, I can finish the assembly.
For the drive roller, I needed a very thin washer as a shim, which I quickly cut from a food container, dropped it on the floor like a genius, and fitted on the drum together with an O-ring, which prevents the roller from moving. And packed like this, I could fit the lid. The tensioning knob is now anodized aluminum as well, and with it installed, I could set the cam disc to stop at the right position.
And there it's done. Quite a bit heavier than the prototypes. Let's see if it works. Oh yeah! The belt stays in place. But that's not it. That was a slightly used belt. What about the used one? It stays in place as well. Nice. And a new one. That stays in place as well. Oh yes! Finally! What a pain this was. But it's finally working. Oh yeah! And with this done, it's time to finish up the rest of the machine, because due to the slight design changes of the main roller, I also need to adapt them here.
That's mainly the drive block that needs to be shortened by 5 mm. Easy task. Unfortunately, this meant that all my sanding spindles now were too short and I had to remake the lower section for all of them. At least that was a fun evening of turning. While disassembling the machine at the beginning to disengage the oscillation, I noticed some other parts that needed improvement. The slider block that makes the height preset was upgraded to steel due to friction issues with the plastic part. Once again, I did that with just a lathe. And the guides came a bit loose, so I replaced the wood screws with bolts and lock nuts. There it's working smoothly again. Everything's done and the machine can go back together and set up. The belt tensioner gets its 3 feet for adjusting the sanding plate square and keep everything rigid. Speaking of the sanding plate, like before, it's just a steel plate bolted to the front.
I also thought about a low friction graphite backing like it's on here, even bought the material, but it has a little bit of softness to it, and for edge sanding I prefer a solid backing and decided against it. The tensioner has one more additional adjustment at the idler roller, because the sanding plate is square and the roller is not, but now that's adjustable. Now what kind of upgrade are these big chamfers on the rollers? Basically, they just nicely guide the belt onto the rollers, no matter how I try to put it on. Before, you would always get caught up on one edge or the other. It's such a small detail, but this being a frequent interaction with the machine, it's such a high quality feeling when it's just nice.
Time to fire it up, and it's running great. After 1 minute, the tracking looks still good. So what about actual sanding? Well, that looks good too. Outer contours against the plate and curves against the idler and drive roller. Everything as expected.
A bit frustrating is that after all this work and failed parts that went into this, the final result is super boring to watch. But the machine is working and that's what counts. I'm very grateful of being in the position of making machines like this, but it wouldn't be possible without the sponsors. So check out the links in the video description, show them some love. They also show some love back, because Proxxon is giving away 5 of their tools to you. You can win the little angle grinder, the belt sander or the tube belt sander.
If you win in the giveaway, you can choose between one of the 3 machines and Proxxon will give it to you in a box with 2 batteries, charger and a few consumables. But if you're not a battery type guy, there are also carded versions available.
To enter the giveaway, just post a comment saying, I want to win a Proxxon tool. That's it. Everybody can participate. And in 3 weeks, I will randomly draw 5 winners and try to contact you. Also, did you already know about the Proxxon tools and have them at home? Do you like them? Let me know in the comments as well. Since I have them, I find myself using them everywhere and I will never give them back. I'm also not done with this machine yet. This T-Track is there for a reason, because next is building accessories for it. I have some great ideas in mind, but since this took so long, this will be in future videos. And this one is over. Goodbye.